we're starting a bit late. I was this conferencing tool sometimes nowadays, because of concurrency issues, sometimes it gives us a lot of trouble. But all in all, we are here. So I did set the whole stuff, but I wasn't able to get a clear representation. Yes, now maybe one or two updates first. I did, we had a cut last week. I checked, not so many people sat for the cut. Not so many people sat for the cut. Maybe you let me, those who did not do the cuts should get in touch so that we see what we can be able to do. So that we move on smoothly, because we don't have a lot for the semester, and therefore we need to move with a lot of speed to streamline a lot of issues that are pending. Okay, issues, cuts, and all that are pending. Yes, now I want us to move from what we were doing last week. That was we have looked at diodes, and we looked at the uses of diodes, how they function, and probably the mode of operation and construction. So I want us to look at transistors, which is still a part of diodes. And therefore it means if you did understand quite a lot of operations of diode, then really we don't have trouble, we'll not have trouble discussing transistor. We'll just move through it very fast, maybe apart from the mathematical calculations that might come on a little bit later through the whole process. Okay, so transistor is basically a reorganization of what diodes are. Remember, diodes, we were just picking a P and an N together, and through that process we are able to form a diode. Now, what was interesting is the formation of depletion layer, okay, and biasing processes, forward biasing, reverse biasing, and how they lead to different types of currents, saturation current, forward current, and so on and so forth. Okay, so here we're going to do we're going to double the configuration. Okay, it's like we are going to bring up on board an N and P and an N, or a P, an N and a P, to form what we'll refer to as a transistor. So we're going to run through the construction, the transistor construction, then a bit of uses, then maybe some other time we can look at the calculations that are involved. So transistors have really changed how we do computing, and how computing or electronic devices are constructed and how they finally operate. So it has really transformed that sector up to this particular point where we are. So what are these transistors? What are these transistors? So that is a history on how those people who came up with the initial ideas on how these transistors could be constructed and how they could revolutionize the computing world. Okay. Now, so that gentleman who has been very, very, very fundamental in these particular processes, and among other things that is commonly referred to as Moore's law, is the predictability that he made of how integrated circuits will look like going forward in the near future. How much of these products or how much of these pieces of elements could be put together to form a circuit that we later refer to as an integrated circuit. Okay. So by definition, a transistor is an electronic device made up of three layers. So the three-layer transistor is also known as the bipolar junction transistor or the bipolar junction transistor. So how is the construction of a transistor taken care of? How is the construction of a transistor taken care of? So we can either have a PNP transistor or we can have an NPN transistor. Okay, so we can have a PNP or we can have an NPN transistor. Now, these three terminals now I've just seen the chart from George. The makeup cut I'll organize once I know those people who did not do the cut, and then from that list I'll choose people who have valid reasons why they did not sit for the cut. Then I'll organize a cut. I don't want to give it to one person today, tomorrow somebody else come. So I want to organize for all those people who missed the cut, but of course with valid reasons. Okay, valid reason. I don't want to you miss a cut because of network connectivity, or you missed a cut because you could not trace it within the portal. No. Yeah, so once I get the list of those who missed the cut and we get the people who missed it validly, I'll organize a cut and then we can move on from there. So don't worry, if you missed it validly, just get in touch and we'll compile the list, then I can share the cut to those specific people. Okay, so I'm saying that the construction of a transistor will take that format, PNP. So it's beautiful that we know what P is, we know what N is, or NPN. Now, these terminals that are going to be formed from this transistor construction, we have names for them. Okay, we have names for them. So depending on the type of transistor in use, later on I'll introduce a transistor in the form of what we call field effect transistors. So field effect transistors will not have similar characteristics like the BJT or the bipolar junction transistors we are looking at now. So they'll take a different format slightly, but they are not common in terms of construction. They are not common. So therefore, the primary construction model that we give a lot of attention is actually BJT. Okay, so we have three of these terminals. We have what we call the emitter. We'll always give it an E Then we have what we call the base. We'll always give it a B. And we have what we call the collector. We'll always give it a C, depending on the type of model or the type of construction that you come up with. Okay, so it looks like two diodes that have been put back to back. Okay, if you look at it keenly, it's like we have two diodes that have been put back to back. Okay, so the circuit symbol for this type of transistor, whether you're talking about PNP or you're talking about NPN, is mentioned below there. Okay, so this is a circuit symbol. That is the circuit symbol respectively. So you look at how the terminals are arranged. You look at how the terminals are arranged, and especially the associated currents. Okay, the associated currents. We have IE for emitter current, IB for base current, and IC for collector current. Now, those type of currents are associated with each terminal there. Okay, so in terms of magnitude of currents, IE is the largest, followed by IC, and then IB. So as we mentioned previously, that the amount of current we are going to experience in this type of circuits will be much dependent on the level of doping. How much did we contribute through the doping process? Okay, so that's what will dictate the number of the amount of current that each particular region experiences. So we normally say that IC is equals to IE is equals to IC plus IB. Okay, even if you look at how the arrows are moving, okay, if you check how the arrows are moving, this is coming in, this is going out, and that is going out. Okay, on this other end, we have a similar approach. IC coming in, IB going in, and IC IB going out, and IE going out. So IC comes here is equals to IE plus IB. That's the same component that we had mentioned in catch-off flows. You remember the junction rule? That is still the same content that we are applying here. So a current that is coming through a junction is equals to the sum of currents leaving the junction, or rather, the sum of currents coming into a junction is equals to the current leaving the junction. So that is the same concept that we are trying to talk about here. So in terms of doping, it means, therefore, that the emitter is highly doped or heavily doped. Okay, emitter is heavily doped. The base is, in terms of doping, very low, and then the collector, in terms of doping, we normally say it is intermediate. Okay, is in between. Okay, not bad, not so much, is just in between the two there. So those are the construction parameters that you'd look at or you'd approach once if you have to construct a transistor in form of a BJT. So the same things are presented here. Just what I've mentioned, how the terminals will be arranged. Okay, how the terminals will be arranged. So the circuit symbol is there. So if you look at this, BJT, PA, and P. Then the arrangement there. Now, so why do we call this category of transistors BJTs? Why do we refer to this category as BJT? Now, this term refers to a scenario where, do you remember when we were talking about conductors, insulators, semiconductors? We are talking about not NP, but NPN type of semiconductors. Okay, so bi means two. Okay, so we are using both electrons and we are using the holes as charge carriers in this type of transistors. Okay. So I'd mentioned there are two types of this type of BJTs. You can either configure an NPN or you can configure a PNP. So it depends on which configuration model you will prefer. Later, I'll introduce some basic differences that do exist. Okay, can introduce some basic differences that do exist between the two. So what does the three terminals perform in the whole of this particular process? What are these three terminals perform? And that is where some of the names originated from. Okay, that's where some of the names originate from. So you can see from the slides there what the emitter does, what the collector does, and what the base is supposed to do. So that's how the operation is supposed to be working. You can compare it to a water pipe or electricity, or whichever model that, or whichever simulation scenario you can put it into. So the ability of electrons to flow from the emitter to the collector through the base is what will determine the functionality of the transistor. Just the same way we are struggling to ensure that in a diode, we can break the depletion layer and move the electrons through the depletion layer to the other end. So that is the same thing here. Now, fortunately or unfortunately, in this particular process, our depletion layers are going to be many, because in between the emitter and the base, that region there, we're going to have a depletion layer. Remember, these are NPN, just the same way the connection was done before, that are still being connected. So here also, we're going to have a depletion layer, okay? And here also, we're going to have a depletion layer, okay? That particular point there, okay? So the barrier potential in each of those depletion layers will also contribute to the proper functionality of the transistor itself. Okay? We're going to relate them mathematically using formulas and see the association that exists between those two different, not those two, but those three different barrier potential or depletion layers. Okay? So if you're taking notes and maybe I'm too fast, then you let me know. Okay, so I've just mentioned that. So the architectural design of BJTs will take that shape. And in each, we are going to have a PN junction or a junction. Okay, we're going to have a junction. Now, the architectural design has a substrate. A substrate is like an insulator, like an insulating material. We'll see how, when we'll be looking at the field effect transistors, how the N channel is formed. We'll talk about what an N channel is, and we'll introduce the concept of substrate in a more detailed concept, as a more detailed concept. You can see the junctions I'm talking about. So base collector junction, base emitter junction. So I've explained a lot of that theory based on the architectural design. And I'm sure we still remember 0.7 and 0.3. They're very, very important in semiconductor theory. They are like our standard units. Okay, they are like our standard units because most of the time, germanium and silicon the preferred materials for these construction processes. So when we mention the base emitter, when we mention the emitter, the base collector, then we really know the amount of voltage we are talking about here. Okay, so for these transistors to operate properly, I say that the voltages or the barrier potential will have a very huge effect. So therefore, we really need to have correct DC voltages, or rather external voltage supply that will be able to trigger this process correctly. That is in comparison to what the barrier potential voltage is representing or is presenting to us. So regions, I'd mentioned that. When you are looking in introducing transistors. So in terms of the doping levels and of course the amount of current. To see the operations of these structures, we have to bias these transistors, whether NPN or PNP. We have to do what we call biasing. So this is how the circuitry device is supposed to be configured, or this is how the circuitry device should look like. Okay, so you look at the where the E is, where the C is, and where the B is. Okay, so now RL on that particular circuit there is the load resistor, and it's connected through the collector terminal to determine if there is an effective flow of current in that particular circuit. Okay, RL is to determine if there is an effective flow of current in that particular circuit. VCC is referred to as the collector voltage, and VBB is referred to as the base voltage. Okay, so as I mentioned before, in between the terminals there are specific voltages that act or provide what we call the barrier potential. So you can see VBE, you can VCE, and you can see VCB. Those are specific voltages that are in between those three terminals. Okay, so we're going to use them to compute mathematically how much voltage do we need through C or through B to allow this particular transistor to function properly. So there's another set of configuration. I'm going back to the other one so you see the difference. Common base NPN. See where the base is, the base terminal is. See where the emitter is, and see where the collector is. That point there. This is where we are supposed to, if we are earthing this particular circuit, that is the point where we are supposed to earth it. So we say the base is common to both the emitter and is common to both the collector. Okay, so emitter is common to both the base and is common to both the collector. So that is another configuration. Then finally, So that's another configuration. There's another configuration. Common collector. That's why the word common is here. It's common to the emitter and is common to the base. So when you go maybe after the class or when you are doing your revision, you will research for me the importance of these configurations and how they differ from one another. And also you will also look at why we have an NPN and why we have PNP and which one is preferable and preferable for which operation or for which type of configuration. At what point do we say we prefer NPN, or at what point do we say we prefer PNP configuration? Okay. So some of these things I'd mentioned. So if something that I'd mentioned appears, I'd just circle it or underline it as we move on. So check how the configurations have been done. Check how the configurations have been done. The introduction of those voltages. Okay, the introduction of those voltages. If you are drawing, so I'm sure we understand the concept of biasing. When do we say a particular terminal is biased in a forward dimension, and the other one is biased in a reverse dimension? I'm sure we understand that concept up to this particular point. So when we say this particular terminal is forward biased, this one is reverse biased, we know the reasons. We know the reasons as to why we put up that particular statement. So what are the importance of this type of biasing? Why do we need this BE to be in a forward biased connection? Emitter is the one that is heavily doped. So much electrons in that particular region. So we are interested in pushing the electrons through the base to the emitter region, to the collector region, sorry. And that is why we are reverse biasing the C region. Okay? So that the electrons that are flowing here can be able to go through this particular circuit in that manner, being pushed on this end, being attracted from this particular point, okay, and then they can be able to go through. That's the measure or the purpose of this biasing process. That's why we bias, because we want a complete flow of charge carriers in this particular circuit. Okay, those three operating region is what make a transistor what it is. It is what make a transistor to behave like an open switch. Is what make a transistor to behave as a closed switch, and it is what make a transistor applicable in switching on and off very large circuits, and is what make a transistor being in a position to amplify signals. Okay, so transistors will operate in those three regions: cutoff, saturation, and linear region. So linear region is controlled. Okay, controlled. So later we look at how those three regions end up giving transistors the properties that they have, or the ability to function in those specific roles, as I mentioned before. Okay, a switch, an amplifier, okay, and so on and so forth. Okay, so but maybe before something just to mention as we move on, you'll check on how this operation is supposed to be done. So this, I've mentioned that this one is open switch. This is closed switch. At linear region, also sometimes referred to as active region, this is now when transistor will operate as an amplifier. Okay, that is when the transistor will operate as an amplifier, meaning that a very small amount of incoming signal or input voltage will really result into a very large output on the other end. Okay, so you'll check and share with me or compare how we achieve those three processes. Okay, how do we achieve those processes? What do we do to ensure the transistor moves to cutoff? What do we do to ensure the transistor moves to saturation? And what do we do to ensure the transistor remains stable or remain in active region or linear region where it has the capability or the power to operate as an amplifier? Okay, so kindly go and check those for me and interrelate the three. Know what exactly do we need to do so that one of these fine days you get back to face-to-face learning, and I send you to the electrical and electronic engineering lab. Then you know what do we really need to do. You know what do you really need to do to achieve those three operating regions. That one enough can be end of semester exams. Okay, if you go back to face-to-face learning. Now, those are type of transistors. I mentioned them. Unipolar, of course, you know, bipolar, both holes and electrons are charge carriers. You know what happens in a unipolar. It is either of the two. A field effect transistors and metal oxide semiconductor basically implement unipolar processes. In fact, metal oxide, we normally call it MOSFET. Okay, MOSFET. That is a metal oxide semiconductor field effect transistor. So it's just an implementation of this, but we'll highlight them a little bit later, just to as we pass through. Okay. So those are types, the classes. In fact, they are classes of transistors. Types of transistors is a little bit broader because you remember when we were talking about diodes, we talked about light emitting diodes, all those type of diodes. So that's the circuit. This is how the biasing should be moving. So you can see VBB, VCC, VB, VC, and VE. Now, VB, VC, VE are the actual terminal voltage for collector, for emitter, and for base, respectively. That is VC, VE, and VB. Now, these ones are the external voltages that do the biasing on those terminals, either forward, either reverse. The resistors on those terminals, RB and RC, are supposed to control excess flow of current. Okay, are supposed to control excess flow of current, so that you can be able to use those ones to control where your transistor is at any given moment, which region is your transistor operating on. You can do that with a transistor or with the resistors in your circuit. Okay, so these are the basic circuits of how a BJT will operate. So VBB is the external supply voltage on the base, and VCC is the external supply voltage on the collector terminal. Okay, so if you see those ones in circuits, you need to remember the meaning. I've mentioned these ones. Just have a look at them. The same thing that happened with the diode at breakdown region is the same thing that still will happen with a transistor here. Now, so that is basically an interpretation of those regions we are talking about, where is the saturation region, where is the active region or linear region, where it's like it's now constant, okay, and of course where is the breakdown region, where probably we cannot control really how the transistor operates and exactly what it does. Okay, we are likely really to control that. So that is just a graphical that is similar to what we looked at in diodes. You remember the diode graph, okay, when we're looking at about the current and the voltage that we're experiencing. Okay, so it's almost the same structure as that. So that is the ratios that are there that interrelate the BJTs and its current, the BJTs and its current, okay? So those are the ratios there. So alpha is basically, if you make alpha the subject, it is IC over IE. If you make beta the subject, it is IC over IB. So you can just provide They are basically ratios between those particular currents that we are talking about. So those ratios are very important to be able to know the multiplier effect. Okay, the multiplier effect, especially when you're doing amplification, the multiplier effect is very, very important to determine how best is your circuit operating. So you need to pick those ones if you are doing the writings. And of course, I will encourage you to do short notes because you'll never have time really to go back to the notes and start writing again, unless otherwise. You'll find yourself time bad when exams will be just about. So in terms of the voltages, those are the interpretations. So collector voltage VC, we can get it from the VCC, that is the collector voltage supply. And we get the voltage, that is IC multiplied by RC. So the controlled resistor on terminal C multiplied by the amount of current flowing through that terminal. Then from there, you can be able to get your voltage on the collector terminal. You can make any of the three the subject and be able to compute appropriately. You can even decide to get VCC from those two other terms. The base voltage, that is VE, you can get it from VE, that is the emitter voltage. Then you add to VBE, okay? That's VBE. We all know these values here, and I mentioned them that when you are talking about the barrier potential, then you will always refer to those particular values there. When you talk about barrier potential, you don't need to struggle doing the computation. Just refer to the known values that we are all aware of. They are standard values that all of us are quite aware of. Now, so the Q point, or what we call the quiescent point, is basically a point chosen to ensure that irrespective of how the input current, alternating current fluctuates, then our transistor can still remain in the active region. We don't want a scenario where if the fluctuation occurs on the input terminal, then the whole of the transistor operation is shifted into a different mode. Okay, so it's basically a point that ensures stability in our transistor operation. So that is what it is in a graph kind of a structure. So it's is in between the two, okay, saturation and cutoff. We don't want our transistor to go into those two regions. So we choose a stabilizing point. That's what the point we refer to as the Q point. So some mathematical analysis on transistors. Some mathematical analysis on transistors. So we say that the voltage divider is, of course, is a biasing tool. Is widely used in the biasing process. So those are approximations on how you can be able to compute, for instance, the base voltage as VCC R2, R1 and R2 are going to come in as a result of the voltage divider, VBD, normally call it the voltage bias divider. Okay, so when it is introduced into the circuit, then we can make this approximation out of that particular circuit. We can make this approximation out of that particular circuit. So those are all just mathematical approximations that we can use in computing some of the variables or some of the items that we have there. So apart from biasing using the VCC and VBB, then you can always bias a circuit using a VBD, voltage divider bias. Now, so I'd mentioned before the two major operations of not operations but applications of a transistor, and so it's either an amplifier or a switch. We know an amplifier should be operating at an active region, that Q point, the region between the saturation and cutoff. Okay, so that is when it's operating or is being used an amplifier. And the amplification process, we expect that any incoming input goes out. Either if you're talking about signals, it is stronger. If you're talking about current, it's bigger, and so on and so forth. Okay, now, so there's basically this classification of amplification process, either as a class A or a class B. A class A transistor, will say, operates fully through the 360 degrees circle. We are talking about the curves, okay? So if you're talking about that, we are talking about this. Okay, so 180, 180, 180, 180. That's what we are kind of referring to. Ignore the writing, ignore the handwritings. The device I'm using is not a good one for writing today. Okay, so that's what we're saying. But now if it is a class B, we only do 180. Okay, we do 180. Then the rest, we normally say this configuration is done in a push and pull kind of scenario, so that to ensure that we are able to achieve the whole amplification process, both for the 180 and 180. Okay, so that's what we are talking about if an amplifier, a transistor is going to be used as an amplifier. But now the next application is when it is being used as a switch. Now, in that scenario, then the expectation is that the transistor should be operating in between saturation and cutoff. Saturation and cutoff, saturation and cutoff. That is when it is being used as a switch. Now, so what I want you to go and look, because I feel I've talked so much, virtual class is very interesting. I can talk for the whole 2 hours or 1.5 hours. It's going to be a bit difficult on my side. Now, so what I want you to go and do to study how BJT is used as an amplifier and how it is used as a switch. Okay, and identify what we call the common application areas. Identify the common application areas. An area that if you're told to go to the lab and write your requirements, and then you're given some money to go and buy, you can be able to explain how this particular process is achieved. Okay, so just read through the notes I'm going to attach on our platform. ZDS is going to have a continuation. Even the ones that I have that continuation of transistor as an amplifier and a transistor as a switch. Okay, so I wanted to go. Yes, that is there they are. So class A operation. So you take your time, just go through them, and be able to report the distinct functionalities. Okay, distinct functionalities between those two things. So that's what I was saying. So what I want you to go and do is when you identify, for instance, is used in low power amplification, then you give me a real example of those low power amplification where applications rather, where a BJT class A transistor will be used to operate at or operate in. Okay, and then the same happens with the class B, and the same happens with the switch. The concept of switching is actually what makes the transistor applicable in memory or in digital circuits, where 0, 1, 0, 1, 0, 1, that kind of memory, that kind of switching, 0, 1, 0, 1, it forms part of how the computer memory operates, how the computer memory works. Okay, so that might form part of your examples on how a transistor is applicable as a switch in computing or in digital electronics or in electronics generally. Okay, but now I've mentioned that apart from switching the large currents, we apply that principle in digital circuit 0, 1, 0, 1. Okay. Yes. So kindly go through that. I'll attach this content on maybe on the platform there. You can use it to read through those content. Okay. Yeah. Any questions so far on what we've taken care of? Any questions so far? As far as what we've discussed is concerned, maybe I can now bring everybody on. Maybe somebody wanted to speak. Yes, Chipkarui, what is the question? Yeah, just say why you did not do the cut, then we pick your name as the candidates to sit for the cut. Donna, Donna, are you there? Donna, are you there? Yeah, now there are a few people here that we need to see their faces. We don't know them. There's a group of these first semester students that never known. I've never seen them. We've not met. Naomi should be in semester 2, I think. Brianson, is it Brianson? Brianson? Semester 1 or semester 2? Helen? Semester 1, 2? Semester 1, new students. So these ones we need to, can you share your cameras? Naomi now. Which family issues? This is digital learning. You can even do the cut while you're sleeping. This one you can even do the cut while you're cooking. This is online. The most interesting learning experience I've ever had. Yeah, you can even do the cut while you're cooking. Uh. Now, meanwhile, we want to see Donna, we want to see Bryanson, we want to see Helen. So Naomi, now, you know, the problem is maybe the students do not know. If you don't do a card, you've given me double work. I have to go and set a new card to give it to you because I'll not give you the same card that others did. How it doesn't really add value to you. Okay. Yeah, George. George. I think we had talked the day before the previous days before the cut. So I know your story. Yeah, so you know when you don't do the cut, you give me double work. I have to go back, set a new cut, upload it to the platform. Okay. Muli, what happened? I'm not. I can't remember. I don't know. So Naomi, type your email address. George, type your email address. Now, Jacqueline, what happened? I don't know. You know, my WhatsApp is so full of now the email address that you are registered on the platform because when I'll set the cut, I'll associate that email address to that people who will be doing the cut. The one that you are registered on. If it is this Gmail one, well and good, but the one that is on the portal is what I want. Now you see the reason Muli Fantasy is giving me that he did not hear about the cat in the morning lesson of last week. You just missed the class. How come you missed the morning one, then you missed the electronics one? Now you see the reason Muli is giving me. Naomi, I'm waiting for your email. Yeah, when the card is announced, you really have to do it. This is one of I don't know what to say, flexible, how much flexible this one is. And I don't think you really need to miss even a class, unless really on a tight process. So if you didn't do the card, kindly just type your email address. Now, also, probably I'll organize this cut next week. We'll have our cut 2 next week, but one. So probably next week, I'll organize this makeup for those people who did not do the cut, so that you can do it within the week. Okay. Yes. So unless there's a different question, I would want you to go through the notes that I've mentioned. I'm going to post the question that I've mentioned here on the forum, and kindly respond to those forums. They form part of the classwork. Remember, the class is 3 hours, so if we do 1.5 hours, maybe the other 1.5 hours should be spent on those discussion forum, the quizzes, and then the rest you can spend in the library reading, like what I've just mentioned now. Yeah, so that we can accomplish about 2.5 hours or so in the learning process. Yeah, so unless there's a question, I'll terminate today's session at this particular point. Yes, so unless there's a question. Yeah, allow me to bring to an end today's discussion. I hope you did your assignment on inductors. I hope you did your assignment on inductors. Picked the relevant notes, and you have them. They form part of our unit as a whole. Yes. You're free to leave, okay? You're free to hang out.